Hi guys, it's Kaswini Ojuku here again. So this is another week. I'll be giving you a breakdown and detailed explanation of what we did at Web3Bridge Cohort 7. This week was also very intense, and we went deeper into writing smart contracts. We moved from writing smart contracts on Remix, and we went over writing smart contract using a Solidity framework called Hard. So I'll be explaining most of the contracts we wrote. But I won't explain all of them, but I will just pick selected few and talk about them and all of that. So this week we learned about libraries, we learned about interfaces, we learned about delegate calls, and we learned about factory contract. So factory contract is like a contract that helps you to create another contract over and over again. Using the same bytecode. So I will help you. I will go through that and see how that works and all of that. So so first of all, we learned about delegate call. Delegate call is a kind of call, a smart contract call, low level call where um, you make a call in a particular contract that calls another smart contract that has the implementation. Now, that contract is where the logic is being executed, but the storage of the contract where you're making the call is being set. So you have two smart contracts. One has the code that does the implementation, that does the logic, while one is the contract that performs the call. So this contract will call another contract to perform the logic, and it comes back to this same contract that made the call to set the storage. So that's how delegate call works and all of that. All right. So without much wasting of time, and let's move on. So I also learned about I know about reentrancy attack, but a friend of mine did something called the reentrancy simulation. So and I had to look through his code, and I saw what he did, and I looked for another way to rewrite the same code. So and all of that. So I look for another way to write the code and all of that. So if you look, let me show you something. So look at this. So we have this bank contract. So this is contract written by a friend of mine. So this is the contract written by my friend, and he made use of Open Zeppelin address and all of that. So he wrote this contract, and and with this attacker contract, you can um, you can move all the funds in the bank contract. So with the attacker contract. So I won't take much time in explaining this. So I now wrote a contract called protected contract. So this protected contract, what I did here is, if you look at the bank contract, so here the logic here is you're sending money to an address before setting the balance to zero. Now, the way reentrancy attack works is this function will make sure that this stuff is executed before this guy is executed. Now, if the contract where this money is being sent to is has logic, like let's look at this attacker contract. you see it has this logic, and this receive function is what gets triggered when money comes into this contract. And it's saying if the address that is sending money to this contract, if the balance is greater than 0, go back to that address and withdraw more money. So this is how this reentrancy stuff works. But now this is what I wrote, protected contract. And I had to bring, I brought the, what's it called? I brought the set here. So I had to set the balance first before I perform the transfer call here. So that way you can't re-enter because the balance has already been, the user balance has already been set before the call is being performed and all of that. So I also wrote protected with re-entrance. So there is an Open Zeppelin library that helps you to protect against re-entrancy. So this is also how to protect your function or your contract against re-entrancy attack using Open Zeppelin. And all these guys are on my GitHub. So let's move over to the main business of today without wasting time on this guy. So yeah, moving over to what's it called? Let's see, what do we have here? So we learned about factory contract, and with that I had to create a smart contract. I created a piggy bank contract. So this is the piggy bank contract. Let me explain what it does. So this piggy bank contract enables user to deposit amounts into a smart contract. So when you deposit that amount into your smart contract, you know the way the conventional piggy bank works. You have a small box where you put money inside, and you leave it for a party. You keep putting money there because you're saving for a particular purpose. So you keep putting money in there, and when that amount, when a particular period of time is reached, you break the piggy bank and you take out all the money to do whatever made you to save the money. So now I wrote a smart contract called piggy bank, where you can be putting money into the smart contract, and while you're putting money into the smart contract, over a period of time, and whenever you withdraw that money, that contract gets destroyed. So that contract will be deleted from the bytecode of that contract will be deleted from the blockchain, while it sends the money to the user, to the person that called this contract. So this is what I did. So I created an event at that event deposit, and it takes in the parameter amount. Event withdraw takes in the parameter amount as well. So I created an immutable address called owner on line 9, and I now created an only owner modifier. So I'll be using this to make sure only the owner of this contract calls the withdraw function. So I now created a constructor. This constructor runs once this contract is deployed, and it sets this state owner variable to emerges or sender, which is the person that is calling this function. And I create a receive function that receives money. So this receive function enables people to send ether to this contract. So that's why it's called external payable receive. And whenever money comes here, it emits the deposit event. So it emits that money has entered this guy. So I now created the withdraw function. So this is why I pass the only owner modifier, which ensures that only the person that created this contract can withdraw from it. And I require that the balance of this contract is greater than 0 before someone can withdraw, hence say no funds deposited. So once that is done, it emits the withdraw event and the balance, and it self-destruct. So self-destruct deletes the bytecode of this contract from the blockchain. Now the previous state of this contract remains, but henceforth nothing happens again. This contract is being deleted, so it doesn't work anymore. So, and this goes to the emerges of sender, which is obviously the owner, the person calling this contract. So I also wrote a function that gets the current balance of this contract and all of that. So now what I was thinking is, I was now thinking, what if there's a platform where like something like a decentralized app as a service, that people can come and create piggy banks where they can deposit funds. You can create your own piggy bank and all of that, and you deposit funds. So that led me to creating a factory contract, which I now made use of create. We learned about factory contract. So well, I read and I saw another way of creating factory contract using Create 2, which is what I did here. So first of all, I imported the mother contract, which is the piggy bank, and this is the piggy bank factory. I created a public state of array that will hold all the addresses of the piggy bank contract. Then here I also created a function called bank count, which will return the number of banks that have been created. And here is a function on line 13 called get bank. So this returns an array of all the banks, like all the addresses that we have been created. So this is the function that performs the main magic here. This is the create a bank function. So this function, the way the create2 function works, the create2 function takes in bytecode and sort. So sort is like a source of randomness that ensures that the address the address it creates for each bank, it's random, is different and all of that. So this is what I did here. So first of all, I was able to get the bytecode of this piggy bank contract. So this is how you get you get the type of this is a contract type. So you get it and you use dot creation code. So this get the bytecode of the contract you want to deploy. Then you get your salt, you pass it to a KECAP 256 hash and ABI.encoded pack. So I'm using block.timestamp. Yeah, I know this is not the best approach. So at first I used address 0, but I noticed that whenever you deploy one contract, you can't deploy again because the source of randomness always remains the same when I used address 0. So I changed it to blocks.timestamp, which I know is not the best way because this guy is already saying avoid using block.timestamp. So I'll figure out other ways of doing this, but for now, to achieve what I wanted at the main time, I use block.timestamp, which the time always changes. It's never the same. That's why I use block.timestamp. So the addresses, the contract addresses I'll be getting for my piggy bank will always remain different. They will never be the same. So I now use assembly and I declare this new piggy bank because I'm returning an address here. So this is what I'm assigning to it. So the create2 takes in this parameter and the salt. And now after creating this, I'll push the address which I'm returning here into this banks array. So this is the banks array here, and this guy is done. So I also deployed this contract. I also deployed this contract on testnet. I deployed it on what's it called again, Rinkibi testnet, and I've tested it and all of that. So yeah, that's basically it. And I also learned how to write tests. So there's this vault contract we worked on, and I wrote a test for it. So this is the test. Where is it? So this is why I wrote the test. This video is getting long, so but yeah, let's continue. So I wrote a test for it to ensure that all the functions are working appropriately. And if I clear this guy and I say npx hard tests, let's see if my test will run. Please run. So let's see. Let's wait for it. What's this guy doing? So while we wait for it, let's see if I can go through what we did here in this test. So this test is taking time. Is it from my system? Sometimes I don't really like using what's it called again? Terminal. This VS Code terminal because it takes a lot of time. So this is what I'm going to do. I'm going to run this test here using my own terminal. So I'll just say npx hard hat. Oh wow, hard hat test. So this is going to be faster here. So let's wait for it. Or is this guy slow because of the recording? So yeah, let's wait for it. All right, so now what this test does here is, let me explain what this does while waiting for the test to go. So I created a vault contract. Okay, the test is running now. I created a vault contract, and this is basically init testing, what we call init testing. So it helps you to test the functions in your smart contract before deploying them and all of that. So yeah, I think I'm gonna stop here so I don't go for further because of the length of this video and so it doesn't get boring. Yeah, so but these are all of the things we learned this week. So we learned factory contracts, how to create factory contract, a contract that enables you to create another contract. We learned about interfaces. We learned about libraries. I think I didn't talk about interfaces. Interfaces helps you make use of the functions in another smart contract. So you specify a certain type of function, the certain type of functions you want to use. So you can import a smart contract without necessarily using all the functions that exist in that smart contract when you make use of interface. And interface also helps you, gives you a guide on what to do. For instance, when you declare an interface and you inherit it in a smart contract, you have to write the implementation functions of all the functions in that interface. So don't think it too much so you don't get confused. Don't think it too much. So that's basically it. Thank you very much for having me. I remain your loyal guy, Kaswini. Peace out.